Hi, everyone. Thank you for being here. So, next slide, please. So, as I would like to kind of motivate this work by just saying that labeled data sets are very important to have, right? We can use them to train machine learning algorithms to basically analyze and understand the data and to make decisions based on the data. However, obtaining labeled data sets could be very time-consuming and expensive. So to tackle these challenges, semi-supervised learning techniques have been proposed. And today I'm going to talk to focus on two of these algorithms, self-training and pre-training techniques. So in self-training, we often have a small amount of labeled data, a large amount of unlabeled data, and what happens at every self-training episode is that, we train a classifier using current training data, and we basically sample a set of unlabeled instances from the unlabeled data and add them to the training data, and this process repeats until there is no kind of unlabeled data left, or there is no kind of, improvement on the classifier on validation data. However, one of the in terms of data sampling techniques, the conventional methods often rely on the classification confidence of the target classifier that we have here, right? And meaning that, at every self-training episode, X% of most confident instances are sampled from the unlabeled data and added to the training data. So the issue, next slide, please. The issue with, the limitation of this sampling technique is that only unlabeled instances that match well with labeled data are selected at every self-training episode. And this basically, and this way the model may fail to best generalize to the entire sample space. So the key contribution in this work is that we instead of having this predetermined rule-based sampling technique, we would like to learn a data sampling policy during this self-training process. So in terms of pre-training, as you know, pre-training is a very effective way to initialize the weights of neural models. And we often have an encoder and a decoder, and the network learns by trying to reconstruct its input, right? And so once we we train such a network, this encoder part can be used to fine-tune the network with respect to the target task of interest, right? And using that small amount of labeled data that we have. So one of the limitations of this work, this technique, is that this, for the encoder part, right, the same neural model should be used in both pre-training and fine-tuning steps. And we are the question of decoupling these two steps is like another contribution of this work, right? So the goal of this research is to develop data sampling techniques that have these characteristics. They should not be predetermined, and they should be able to explore the entire data space. They should be able to make decisions based on the classifier behavior and the characteristics of the instances that we have in the data set. And finally, they should be able to separate the pre-training and fine-tuning steps. All right, so this is the general architecture that we have developed for this task. And so the architecture is exactly the same. It looks different, but exactly the same as before. At every training, at every self-training episode, we have create a classifier, we sample unlabeled instances. The only difference here is that we we use this, and we basically develop a neural model which is basically informed by a spaced repetition algorithm, which is like, a finding in cognitive psychology that, shows humans can learn more efficiently and effectively if the learning materials are scheduled for them, spaced over time. And so you can think of it as like a flashcard system, where we have a bunch of queues and we populate these learning materials over these queues through time. So here we have a neural network that is trained using the current training data, but we So the specific thing about like the way that we use unlabeled data here is as follows. We place all the unlabeled instances in the first queue. And when the networks, during the training process, if the network is able to kind of make correct prediction about the pseudo label of the unlabeled instance derived from this classifier, it basically, the instance gets promoted to the higher queues, and otherwise it goes to the lower queues. And so you can imagine that, eventually instances that are easier for the network to learn their pseudo labels will accumulate in the higher queues, and those that are easier will go to the lower queues. And so I would like to mention that, misleading instances occur, right? Instances that home in on wrong queues because of, there are some errors here, like incorrect pseudo labels could cause errors, or incorrect class predictions could cause errors. So we tackle these kind of challenges, this problem by kind of this greedy data sampling technique, which basically at every self-training episode, we select instances of the queue that most improve the performance of that classifier, of the target classifier on validation data. And this basically, to some extent, it reduces the effect of those misleading instances. All right. So here is we evaluate this technique on 2 data sets. Sentiment for like 2 tasks, sentiment classification and churn classification. Churn is a little bit kind of more difficult than sentiment, and it has like many interesting linguistic characteristics, which I don't go through them now. But so this is the kind of performance of the base classifier, as you can see from the performance across the 2 data sets. And this is performance of standard training. These 3 are kind of 3 different pre-training algorithms, and this is the Leitner-based self-training approach. And the performance of our model is significantly better than the best competing baseline here. And the one interesting point here is that we observe some improvement using standard training on IMDb dataset for sentiment classification, but no improvement here. So this could be because of as I said, the standard training is the architecture that I showed you at the beginning of my talk. And this could be because of the failure of the standard training to kind of explore the data very well, or the classification errors that kind of reinforce each other, or maybe because of the highly imbalanced class nature in terms of the churn data set, because sorry, I should have mentioned that churn is a kind of is a term in marketing discourse that basically indicates whether a user intends to leave a brand or not. For example, if someone says, I'm leaving Verizon for T-Mobile, that's a churny tweet. So in our unlabeled data set, the fraction of these churny tweet, the positive instances, are considerably smaller than the negative ones. All right, next slide, please. So we basically look at 3 questions to understand like in the context of self-training challenges, how this model works and what are the kind of takeaways. So the first question that we ask is that what's the issue with the highest queue? Because we found that almost always the kind of the Leitner system doesn't sample instances from the highest queue in the Leitner queue, right? So we wanted to understand why this is the case. The second question is that when we are creating a sample, when we are sampling unlabeled instances, do we need to have diversity there or not, and to which extent? And the last question is that can we improve this self-training approach that we are proposing? All right, in terms of the first question, to answer that, we basically just compute how well the kind of instances in the highest queue match with current training data at every self-training episode. And we compare it against the kind of the extent of matching for the designated queue. As you can see here, so the blue bars here, the first and third bars, are kind of the similarity, the average similarity between instances in the highest queues and the training data. And the orange ones, the second and fourth one, are kind of the corresponding values for the designated queue. As you can see, instances in the highest queue match much better with the training data, and that basically might explain why they are kind of less informative than those that are in the designated queue. All right. So in terms of queue diversity, we basically compute the extent of diversity that every queue, instances of every queue introduce when they are added to the training data. And as you can see here, like this is the kind of diversity, and this is like, the average across all the self-training episodes. As you can see here, the designated queue has a considerably high diversity as compared to the rest, to other queues, specifically like, the highest queues. Like this is for IMDb. And this basically showed that it is important to have a diverse set of unlabeled instances to get some improvement. And actually we used this result to kind of improve the performance of our model by kind of 3 to 4 absolute point in F1 by kind of, developing a even more diverse queue using these Leitner results. All right, in terms of the sampling policy, so the question was that how can we improve this sampling technique, right? So for this experiment, we basically took all the instances that home in on the same queue at the end of this training process, right? We took all those instances and computed the deviation that exists in their movement patterns, right? So as you can see here, this plot shows that kind of average deviation across all these self-training episodes. So for queues that are in the middle, we observed a greater deviation in the movement patterns. But for those that are at the kind of lower or higher queues, there is no much deviation. And that basically explains, and given that, most of our, like, the queues that most improve the performance of the model are like from the middle to higher queues, this basically explains we can kind of further look at these queues to kind of, do fine-grained sampling to further improve the performance of the model. And here is a running example. So we have, I'm showing like 4 instances here who, all of these instances home in on the exact same queue at the end of, like 3-4 iterations. And as you can see, although these instances all go to the same queue, but their movement patterns are considerably different. And therefore, we might want to kind of treat them differently, right? So to conclude, we presented an effective formulation of spaced repetition techniques. And in terms of future works, we would like to kind of definitely look into the, finer grained queue level analysis to see if we can get improvements there. And also we kind of, we use the kind of a neural model for the kind of Leitner based self-training, and we're wondering if we can kind of use other iterative training approaches, such as boosting techniques, to see if we can obtain some improvements using those algorithms. And obviously, we can kind of apply this technique to other areas where we have limited amount of data available. Thank you very much, everyone.
Okay.
Okay. So thanks for a very interesting talk. I had like 2 questions. One is, does the seed data, the supervised training data that you select initially, does it matter very much? So in other techniques like bootstrapping, selection of seed data matters, and what percentage of the data was the starting seed data? And the second question is, did you try anything related to data augmentation to enhance the size of your data set, to improve semi-supervised learning?
So two questions. One is that whether seed data is important in kind of in this sort of techniques, and the other one is that have you used data augmentation to kind of compare against these models? So I answered the second question first. No, we haven't. But yeah, that's a good kind of way to approach these problems. For the first question, yeah, seed data. I guess we actually created 5 sample seed data sets for each seed data for each data set, right? And we observed variation in terms of performance when we are kind of using different seed data. That's obviously one of our results.
Is there any confirmation bias selection for seed data matters in the final model that you
Yeah, so the result of the final model kind of changed, and we are kind of here, we are reporting the average over all those 5 samples that we had.
Any other questions? I have a question. So this is a very interesting approach, and I'm just curious, how do you see applying this to some other domains? For example, automatic speech recognition. How would this work in that? Have you guys tried anything like this, or how would that work?
No, we haven't tried it on kind of speech recognition or any type of speech data, but I applied it on a couple of biomedical informatics data sets, and we observed some improvement in kind of specifically in information extraction techniques, but the question of extending these sort of semi-supervised learning techniques to any other area is as far as you have a small amount of labeled data and a large amount of unlabeled data for any task, you would be able to kind of apply these techniques to them.
All right, thank you very much. Let's thank the speaker.
Thank you, everyone.